Okay, hi folks, very good morning to you. Happy having you here on board on our Taben webinar. So I'd like to introduce myself. My name is Elmar. I'm responsible for technical hotline and services, assisted by Christoph at the control panel in the background, assisting me with the camera stuff and the audio control panel. Yeah, what are we doing today? We are presenting finally basics of heating control, and especially we care about, let's say, flush mounted heating actuator used as a heating controller. I will show you how tiny, how fancy this solution is finally, how invisible it is finally, and how to do, what are the impacts of the ambient temperature rather than let's say the other stuff. And we talk about, let's say, at the end of this webinar, a few bit about RF secure. So you can get this heating controller as well if you want, as well as a secure option, RF controlled. Flush mounted option, sure, tiny, small, and with some, let's say, additional tools like external inputs. We see how it works and how it runs. So first of all, we like to show you, we like to make you acquainted with, let's say, a heating system in principle. So probably you haven't seen or you haven't thought about how it works finally. We do have here, on that stage here, we do have here a heating system, heating pump, bringing up the warm water into the system finally. We do have here valves, motor-driven valves, terminal valves. However, we do have here RTR, room temperature controller, which gives you the feedback, how is the current situation in the room and how is the heating valve to be positioned that finally at the end of the day you get the reasonable temperature into the room. And we do have here, the blue line here is the flow backwards, so that means this is a cold water finally coming back from the rooms to the heating system, and here in the heating system heated up again. So it's a circle, a cycle and a circuit finally, and this runs permanently, depends on demands in a room. Physically it looks like that. We do have here some radiators like here, and we do have here these pipes, which mostly are in the floor, in the street of a building. And here we do have the flow forward and the flow backward, which you can discover here with a black arrow, the blue arrow and the red arrow. And this is circulation, how it works. When it comes to the control commands, to the heating value finally, so you can operate with two different valves. We have in the market, in the KNX market or in the domestic market, we do have here terminal valves, which needs 240 volt or 24 volt, however, or we can use as well like our KOPs, our motor-driven valves as well. Highly recommended if you control, so radiators like here, so there, KOPs control, for instance, a motor-driven valve is absolutely accurate and precise to control the heating value and to control the heating perfectly and absolutely precise. Terminal valves we recommend for the warm water underfloor heatings. So because warm water underfloor heatings are from their, let's say, control characteristic rather slow in comparison to these radiators, which we do have here on the left-hand side. So how the control principle finally is. We discover here, we do have here some impacts from the ambience. So that means depending on the weather, which we do have, depending on the insulation or isolation of a building, for instance, we do have some impacts into the room, as well as we do have some impacts from, let's say, some technical stuff, like lamps, like audio systems, like people. So if a person, for instance, is in a room, depends on what he is doing. So 100 watts of warmth energy per hour is, let's say, a rough average, just that you know. Depends on how hard you are working in the room, however. But these are energy gains which you bring as a person into a room and which has an impact on the entire room temperature, and you have an impact on the room temperature control cycle as well. We do have here a RTR, so a room temperature controller, which could be Eon, which could be Ramses from Taban, for instance, which measures finally how is the current situation in such a room, which we do have here, for instance. This is an office building, so measuring how is the current situation, how is the status, for instance, if there is a window open, yes or no. So if you have a smart RTR, so then you can link finally a window contact directly to the RTR, and the RTR controls comfort mode or frost protection, for instance, in the time, during the time when you do a natural airing by opening a window, for instance. Yeah, and so this room temperature controller is measuring finally every second how is the current situation inside of the building. He knows the set temperature, your desired temperature finally, which you adjust, which you preset, and the difference is calculated finally as a heating value, which is given to the valves. Again, either a motor-driven valve or a thermal valve, however, and then we open or we close, depends on the situation, a radiator, the flow forward, the warm water is coming in, flowing into a radiator or in an underflow heating, however, depends on the situation finally. Then we do have some impacts because the radiator now is emitting the reasonable warmth into the room, and during this procedure, the RTR permanently measures, so how is the procedure, how is the situation currently in the room? Do we need more warmth? Do we need less warmth? When we come closer to the desired temperature, for instance, so the heating value will be reduced. I will show you in a few minutes in a live act. And these impacts all together finally are coming together in a cycle. So that means we do have the impacts, and these impacts influences finally the RTR and gives a new, let's say, control value, a heating value to the valve. That's the cycle. Sounds pretty simple. Yeah, basically it is pretty simple, sure. And if you have really a smart solution, we do discover here this chart, and this chart here finally is a heating curve. So that means the heating system. So it could be oil heating, could be a gas heating, could be a heating pump, however, grading your heating, which is required for a building. And if you have smart controllers / smart actuators giving you the highest activating value, and you have the reasonable heating gateway, which Taban do have, yeah. So we can have a massive impact on this heating curve. So that means no demand, so we can lower this curve. So we actively reduce the energy demands and we save actively a lot of energy. If the heating actuator give feedback, we have currently all channels, all heating circuits finally requires a lot of warmth. So we can shift automatically with this heating gateway, we can shift this heating curve 1 or 2 degrees up. And so we do have the required warmth into the room. So automatic adaptation, highest degree of energy efficiency and highest degree of comfort for you. So to give them a face to this heating principle or this heating system, we do have here, for instance, RTR, which is our Eon, for instance. We do have here our Cheops, which is controlling here the radiator valve to open to close the heating circuit, and the impacts coming from the outside, coming from the inside, from technical staff, from the people inside, and so on. There are different options, basically, coming from that side. So the valves, okay, it's your decision, which you want to use, which you intend to use. However, it's a matter of price as well. So thermal valves are by far cheaper than a motor-driven valve. Motor-driven valves are by far more accurate, like thermal valve. So it's up to you what you think, what you desire, what your client desires finally to have. Then we do have here 2 options. Either we do have here these DIN rail-based actuators. So coming, the control command and the heating actuator is positioned in a DIN DB board, for instance, or our content of today, the flush-mounted actuators, which you can hide somewhere in a flush box in a wall, however. And the room temperature controller, for instance, either with the external remote, so you can adjust your set point, or here you have RTR, no, but you have the temperature probe, which is inside here of this push button. And with this room temperature, which is measured here with the Eon 102 in this case, you address it to the heating actuator, which is to be set as a controller, and then the heating system is running on its own. Discrete, noiseless, because there are triacs inside, and that's it. Yeah. So that's how it could work. There are the options finally. And when I open this slide here, it's just to make you acquainted so how underfloor heating is working. So you discover, so the principle, the main principle here is the same like we do have in radiator control, but the warm water is coming from the underfloor as well. That's how it can look like in reality. So these pipes here, which we do have here, these pipes are going to the rooms and back from the rooms. Here are the thermal valves finally. And in this example, for instance, we do have here our underfloor actuator, which allows to set per channel 3 of these valves, of these Theban valves, for instance. So if you have a big space room like we do have here in this industrial building or in this public building, however, so then probably the circuit is too big for just one heating circle. So probably you have to control 2 or 3 together in one room, controlled by one heating actuator and one controller especially. So, and then you can link 3 of these valves together on one channel of this heating actuator here. So just that you know how it works. Yeah. In this case, I want to make you acquainted about, so for underfloor heating, we definitively, I mentioned it, we recommend these thermal valves, yes. Motor-driven valves, okay. The efficiency is not better, so that means if you use motor-driven valves for underfloor heating, the underfloor heating is not more precise in comparison to a thermal valve. That's just a matter of price. Motor-driven valves are more expensive. If you want to invest, always welcome. But if you invest, then invest in our Theban motor-driven valves, and then you will have the reasonable result. Myself and my staff in the telephone hotline pretty often get the demands or the requirements. Yeah, can you give me a recommendation? So if I have underfloor warm water heating, does it make sense to reduce the temperature during the nighttime, for instance, in order to save energy? I would like to say, out of some experience, if you do so 1 or 2 degrees down, that's it, not more. Yeah. Otherwise, it is not that efficient anymore, because it depends always on the screed, which we do have, the insulation, which we do have. And when we reduce the temperature too much, so you need next morning a long time to heat up this system again. And so the energy efficiency is not that good. So 1 or 2 degrees maximum night reduction, that's it. Yeah. Recommendation for, with experience of more than 25 years. Some ideas or some, let's say, important things which I want to share is now what you need to know, because we pretty often get as well the questions into the telephone hotline. Yeah, my heating system is not working so properly. I do have 2, 3 radiators in a room. One radiator is getting warm, the other one is not that warm, and the other one is so somewhere in between. So they are not constantly, let's say, giving the same warmth into the room. What could be the reason? These are reasons in 99% which you can't manage with any kind of settings in the KNX application. This is mostly hardware. So for instance, hydraulic adjustment. This is a valve which you see here, which is directly installed on a radiator. Here on this side is the valve installed. You have here, let's say, a small ring with a pitch, reasonable. And upon you move or you put the reasonable terminal valve or motor driven valve upon. And there is a small screw, and with this screw you have to do, not you, but let's say the heating specialist, he has to do the hydraulic adjustment. What does it mean? So the water flow through this radiator has to be equal to the radiator next and the over next. So that means that all radiators have the same amount of warm water flowing through the heating system. If this hydraulic adjustment is not made properly, yeah, you do have such kind of effects. And you can't manage it with any kind of, let's say, KNX, application modifications, and so on. So forget this. This is a hardware problem which has to be solved from the heating specialist. Or probably you do have, this is exactly what could be, for instance, as well. So you do have a radiator, which just mostly in the corner where the valve is installed. So there you discover there is a certain warmth, but the rest of the radiator, you feel it's rather cold. So it's not constantly the same warmth which the radiator emits into the room. So what could be the reason for that? Pretty simple. There could be probably in older systems, or probably even in new systems, there could be probably air in the system. Basically, these tubes are filled with warm water, with liquid, and in this circuit, there should not be any air, because then you do have some noises which sounds like bubbles, yeah? And this affects finally that such kind of heating systems, could be the underfloor heating, could be the radiators as well, is not constantly giving you the same warmth on into a room. So what does it mean? You have to do, to bring out this air. On this side of a radiator, you do have a kind of a valve which you can open with a specific tool. You put a mug or such underneath, you open that for a while, and then mostly the airstream is exiting this system. And when you have permanently water flow, then you can close this pipe as well. And then you do have, let's say, a system without any air in the system. And after a short while, a really short while, half a minute, maximum a minute, this radiator should be heated up constantly in the room, and then you should not hear any, let's say, slight bubble noise or anything else. Again, such things you can't manage with KNX application settings. This is hardware. And this is some which you need to know because from time to time we get some questions into the telephone hotline. What can I do in case if? This is hardware, and this is, again, it's not your job. This is the heating specialist who has to do that. Yeah, when then another question is finally, so what kind of control command is to be recommended for the different heating systems? So when it comes, for instance, to underfloor heating, what is to be recommended there? When we talk about heating actuators, so or heating systems like radiators, so what is the most best control command to control it really precise, accurate, energy efficient? And when you give the reasonable answer, so we do have for radiators, PWM control is most best because it's rather fast, adaptive, and so ideal for rooms like here, conference rooms, office rooms, and so on, or private, your private area in your flat, however. And so for these purposes, so PWM control is most best. When it comes to underfloor heating, then you do not need such accurate precision in terms of the emission of the heating warmth. And in regards of, let's say, the speed of the heating, underfloor heating requires a little bit more because of screed in your room and the plates upon the screed, however. There is a slow process. And due to that, in this case, for underfloor heating, we pretty often use this hysteresis control, which is more than good enough, more than precise enough to control it really, let's say, in a comfortable way. Yeah, you see here some advantages, disadvantages from compared underfloor heating here, radiators, warm water fanners, for instance, or heating fanners, or convector heatings. You see the advantage, the disadvantages here. And this finally has to be decided from the architect what is most best in order to heat up such a room, like a building here. What is most best to control it in the most best way, or to energize it in the most best way. However, advantage, probably you know, and you have to decide now, so what is most best in this case. And the hysteresis control, you have to imagine, so it is, for instance, this is your desired temperature, and the hysteresis control has a certain hysteresis, let's name it as a tolerance, a tolerance below and a tolerance above. And as, let's say, bigger the hysteresis finally is, as more inaccurate the heating finally is, because it's always cycling around your desired temperature. When you lower, when you reduce these hysteresis, so then it becomes rather, let's say, rather correct, I have to say. But then the heating, let's say, activities is rather often. So that means we do have here permanent on, off, in order to keep really this temperature rather, let's say, smooth and rather precise. This setting has to be done, has to be adjusted. This is your part. You have to know, so how is the situation in the room? How fast is this, let's say, heating system? How is the insulation of the room itself? So here you can adjust, right? This is your part, and you do have here in the application of the ETS, you do have here the option to increase or decrease finally the tolerance, the hysteresis finally, in order to get your most favorite temperature into the room. Here you can adjust. This is your turn. You have here the options, any ETS. Or we do have PWM control. And a PWM control is like that. So we do have here, for instance, my set temperature, my desired most favorite temperature, my desired temperature, and there is a kind of triangle which is put upon, so virtually due to electronics and software. And let's assume now we do have here the current temperature, and for that purpose, probably I will show you such how it works in real. Parallel, I will open the ETS. I will start this, diagnostics and group monitoring. Start. Okay, then back to this presentation for the moment. So that means, so we do have here, let's say, a situation, terminal valve, which is here just clipped upon this valve, controlled by the actuator, which is hidden here behind this cover. The actuator, you see, the actuator matches perfectly in such kind of a flush mounted box. There is space for the wiring, and you discover as well, we do have here small, tiny little cablings, which are binary inputs, which are directly linked here to the actuators. And the color, so I've wired it on the background. So with the color of the binary input is red and black, and this is linked to this small fancy temperature probe, which I just sticked here on this cover, which later on I put upon the actuator for the heating control. So now I go back to the heating system. We do have currently 23.1 degrees of temperature, and I try to read now the heating value. It's 001, and I want to read it. So we currently do have here 0 degrees of the heating control command. That's the reason why the valve is closed. There is no demand because my set temperature is exactly what I want to have here in our studio. And what if I do now, I do have here, let's say, cooling spray, and I do now reduce the temperature. And when I reduce the temperature, so it takes a few seconds, then the temperature will decrease. So 22, 21, so and after a while, when we are undershooting this desired temperature, so then we get a heating value which is not anymore 0%. The system will give us finally the new control command. So heating value, should now come. Okay, probably to bring down the temperature again, it's not enough. So, okay, you see now it acts. So that means we're now underpassing or under running finally the heating system. It is a slow process, yeah, a certain slow process. But you see now the heating value turns automatically to 100%. So that means this valve here is opening totally, yeah. So because there is a demand, 80 degrees or 14 degrees now is by far underneath our desired preset temperature. And due to that, we open fully the valve. The warm water is flowing through, the pipe is fully open. And when I do now the other way around, so I put now my fingers upon, so then the temperature will rise after a short while. And then you will discover as well that the heating value will change as well. So will reduce from 100% later on to 80, 70, and so on. This is a dynamic process, depends on where the temperature finally is currently in the system. Yeah, so heating value, okay, we still reached because I talked too much. So you discover here 21 degrees reached, so then the heating value is reduced again. So in the meanwhile, while I have been talking, so it reduced to 78, then to 0. You see how it works, and that's the principle finally, which we do have here. So then exactly here in between, this is your heating value, yeah, which is given to the valve to open or to close. Here we are by far below the temperature. We have a high heating value. And in this example, we are pretty close to our desired temperature. And due to that, it's just a small heating value required finally to open a valve, just let's say 20% or such in this case. And then we just get a little warmth additionally into the room in order to reach finally our desired temperature. So pretty simple how it works, how it acts. And that's finally all what we have to know about. So the main principle is good to know. So how it works, then you know exactly what you are reading finally in the ETS, in a bus monitor. What does this heating value means? Now you know, hopefully. And in the RTR, so in our Eon, for example, we do have here a controller inside, which allows to control, to support the heating control with PWM or the hysteresis control, or in this case we do not need, but heating and cooling and fan control as well is possible. So that's finally the thing what has to be mentioned. Characteristic of the heating, I was mentioning a few slides before, so we can do actively supporting finally a heating system. Even this actuator here, for instance, can give us this actuator here can give us the highest actuating value, so it gives us a feedback. So how is the current status of that? And this as a total amount of different heating actuators or heating controllers which are installed here in the different floors. So you get as a sum, as a result, and with a heating gateway finally, again, so you can really actively, without your activity, you can automatically adapt the heating curve to the demands, to the desires finally, which we do have to control, to climatize finally such buildings, which we do have here in the background. So how you have to read such a curve, I think it could be probably of interest for you, especially for those who haven't get in touch with such. So this is a heating curve which you mostly find in the documentary of the heating system. And the reason is, let's say, the function principle is dynamic. So that means, for instance, if we do have here an outdoor temperature of minus 10 degrees, and the curve, the heating curve is set to K 1.2. So this curve you can adjust. This you have to do manually, or the heating specialist has to do that. Depends on how is the building structure in general, how is the isolation finally of the windows of the room, how much warmth is, let's say, lost, wasted finally through a building which is probably not that well insulated or isolated, for instance. And due to that, the heating specialist has to adjust exactly that curve. let's assume, so this K1.2 is used. So at a temperature of -10 degrees, we do have here a flow forward temperature in this system of 55 degrees of warm water flowing to a radiator, for instance, into a building, into a system. If you do have underfloor heating, be careful. The max of underfloor heating flow forward has to be adjusted due to such a curve to maximum 40 degrees, not more. Otherwise, you will probably destroy the plates which are on the screed in your building. So here you have to distinguish radiator control, underfloor heating control. Okay? So, and let's assume, for instance, you have an excellent building, well is isolated, for instance, with the most best material and so on, like we do have here. So then probably you can set down the curve, the heating curve, to the K043 in this case, in this example. So what does it mean with the same outdoor temperature? We do have here -10 degrees. So, and we do have here approximately 32, 33 degrees, which is as a flow forward temperature going into the room, assisting you, supporting you with a reasonable warmth in the room. Okay, you got it? Fine. So coming to our, let's say, actuator itself. Basically, I want to mention that this flush-mounted actuator supports you for up to 3 of these terminal valves for big space room, however. Yeah. And you discover you do have here this small temperature probe, which you can directly link to such kind of a heating actuator. How we do so? So probably we can get the camera for a second. Thank you so much. So that means, yes, thank you. So we do have here on an actuator, we do have here at the side, we do have here interface, we do have here cabling for 2 binary inputs. Yeah, and this you have just to click it in here. So then like mentioned, in this case, the red and the blue one, you just link to this temperature probe here, and then you tap the temperature, which is measured with this fancy small temperature probe. You see here how the dimension is finally. This is the flush-mounted actuator, which fits directly in a flush box in the wall, and you see the dimension finally, how fancy small this temperature probe finally is. And this has to be wired here directly on this actuator. So this has to be known, and with this combination, this terminal valve, this temperature probe, and this actuator on the left-hand side, you can do your temperature control in a room. Discrete, invisible, because hidden in a flush-mounted box. The temperature probe is you can stick it on the backside of a cover of this flush-mounted box, and that's it. Discrete, invisible, and nobody unauthorized can modify your set temperature, because these set temperatures are adjusted in the ETS. So that means we can do the following. I will make you acquainted with some application settings. And this means finally that, yes, okay. So that means heating controller, the application settings are like that. We do have here the parameters. Put this down, the parameters, and we have here the monitoring. Let's start from that side. So we do have here the channel, let's say parameter settings. So what you can switch off this one here if you like. And we have the option now, for instance, here to decide if we want to have this actuator as a heating actuator, or we want to have it as a controller. If we set it to the controller, so then finally the settings, the heating values, here you adjust individually. So that means in the background, these preset temperatures are fixed. Nobody can modify. Okay, if you have a visualization or such in an entire building, so then with a visualization you can, let's say, modify the desired temperatures, but nobody unauthorized does not have any touch point where you can increase or decrease the temperature. In some cases, it is absolutely benefitful exactly to avoid that, and as well to have a temperature control which is invisible, hidden somewhere in a room. You may probably wonder, so if this small temperature sticked on the cover of a flush-mounted actuator could be such precise. It is. You remember my demonstration here? So it was just a few seconds when I tapped this temperature probe, and in the ETS you could see rather fast the heating value was changing from 100% down to 78 and down to 0%. It was rather fast, less than 1 minute we could achieve that the temperature was measured again and the heating actuator was acting accordingly. So it's rather fast and rather precise, we have to say. The configuration settings, so these, let's say, light reduction and so on, always relates to the base set point. So if we do have here 21 degrees base set point, and we intend, for instance, to use a presence sensor for a meeting room, the meeting room is not occupied. So then, for instance, we give the trigger to the actuator. So go down to standby mode. Standby mode means 21 degrees minus 1.5 degrees. So, you know, 19.5 degrees is standby temperature, or night mode from 21 degrees, 5 Ks down. So we do have here 16 degrees of the room temperatures during the night. So that's how it works, how it operates finally. This one could be probably of interest when you intend to integrate this kind of small, smart and fancy heating control into a visualization. So here you can adjust limit finally. So how is the set temperature to be, let's say, or how wide can the set temperature be modified? Just 1K up, 1K down, or up to 5Ks up, 5Ks down. That's up to you. This you can limit finally in these application settings. Operation mode. After reset, so this is more or less standard. You can either use presence sensors to control such a room. Finally, if there is a room occupied, presence sensor gives us a reasonable trigger, or you can do as well presence button. So that means if a meeting starts, the reasonable person who has invited for the meeting, for instance, give a command on a switch, giving the signal to the outside, room is blocked, and with the same trigger, for instance, we address, okay, now presence, the meeting is ongoing, and we need, for instance, now to have the comfort temperature. So that means we want to have it comfortable warm. The forced mode could be of interest in such a case. If, for instance, we do not get, however, probably the temperature probe is broken or the cabling is broken, however. This is an unlikely event I want to mention, but okay, can happen. But in this case, we can adjust here, for instance, in this unlikely event, which degree of heating value we want to address, we want to send, that the room does not totally cools down to, let's say, a critical point. Yeah, this is just a kind of fallback position. The monitoring time, so this is a matter as well. What you want or what you can give to a visualization, for instance, so this actualization of the current situation in the room. However, this is just for, let's say, control and monitoring purposes. And pump control, so this is, for instance, some could be of interest. We do have here, let's say, a communication object, pump control, and this command finally can control switching channel, switching finally a heating pump if the entire heating system is not, let's say, supporting such applications. If there is no demand in such a room, like here, for instance, lights are dark, nobody there. So why there in this second, let's say, floor, why there the heating system shall be activated, why the heating pump shall move or bring the warm water into this entire circuit. Nevertheless, if the valves are closed or not, you can stop the valve as well and save additional energy finally on the heating pump side, if you want. The interesting point is finally, we do have here the inputs 1, inputs 2. So for instance, input 1 could be, in this case, a window contact. So that means if one of these windows, for instance, is to be get opened, so therefore a natural airing of however, so then you can integrate this contact finally directly to the actuator. You remember, we do have here 2 additional ones, one for the temperature probe and one for the window contact, for instance. And then the temperature is going down to frost protection as an example. Input 2, just input 2 is able to support you with the reasonable option, which you can select here. Just the input 2 gives you the option finally to select temperature input. And if you did so you can do, for instance, here a temperature calibration, could be affected more or less on this, let's say, place where the flush mounted box is positioned, could be affected by probably some technique which is in front of this temperature controller and this cover where the temperature is tapped. So you can do here, let's say, a reasonable temperature adjustment individually. Okay, you see, rather simple, rather fast in terms of, let's say, the communication objects. If I open the communication objects here, what is minimum required? We need the outside temperature. Okay, this is this small fancy temperature probe, which you stick on the flap. And you need the communication object from the actuator. So channel 1 gets the temperature from the outside, in this case from the I2, so from the binary input. This is just to monitor. If you want to know, for my purpose, finally, you want to see that something is working. So either the valve is opening or I showed up in the ETS in a bus monitor, so that you get a certain degree, a certain percentage value finally showing you, monitoring you. So how is the count situation? Probably you are eager to give this information as well on a visualization. That's exactly what is required. The operating mode, you need the current set point, which you can read finally, and the window status you have to link, and that's it. You do not need more. It's really simple, fancy, and you do have here a perfect and, by the way, a noiseless solution in the room. And one thing I want to mention finally, in regards of, let's say, safety. We not just talk about safety in terms of communication. I want to address as well that our heating actuators and our dimmers, by the way, they do have a thermal control inside. So in the unlikely event of a thermal overload, the actuators turn off to avoid any damages. When the temperature is okay, back again, so then the actuator starts again. So probably it was just one shot situation, however. When the situation is clear, afterwards temperature is stable and in a, let's say, acceptable level, so then the actuator comes back and works ahead like before. So just this is not just, again, bus safety, we talk about hardware safetiness as well. Internally, we do have here triacs, noiseless, not auditable, no relay, click and clack and so on, you know that. We just want to have silent, discreet and a safe solution. In some events, I come closely to the end now, so in some events probably you might not have probably the cabling to do an extension in the building, however, but you need the heating situation, the heating solution finally. And what you can do in such kind of project, so you need, for instance, here a kind of a media coupler, which is talking RF secure. This has to be linked, hardwired to the KNX bus system, sure. Then we need here the actuator, the RF actuator. Here we have to apply 230 volt to give them the reasonable power. And then via RF, you send the values, the heating values finally through the media coupler to the heating actuator. You can operate this in secure mode. So that means in this case, this is just to be mentioned, all our, let's say, flush mounted actuators and some more prestigious products, meanwhile, are equipped with KNX Secure. You have just to take this QR code, which you find here on all of our flush mounted actuators, on the Eon temperature controller, and as well, you will find it in the future on our, let's say, brand new sensor. You need just to hold it in front of the camera of your laptop. This QR code is read and screened and finally taken over. And then you can address, you can operate, you can communicate with this, let's say, product in a secure mode. Quite simple, quite excellent. I will end this seminar, this webinar finally with a short and slight example. What does it mean? I want to show finally how you can do it. For instance, if you want to operate, let's say, with the manual, so that means with a tablet or with your mobile telephone, for instance. But in this case, you need the RTR, the Eon, for instance, which is a room temperature controller, a powerful room temperature controller. I open the app meanwhile and just search. In this case, we do have here exactly this situation. We do have here a room temperature controller. We do have here the flush mounted installed heating actuator in this case, controlling this value here. And I have discovered now there is Eon 108, which is communicating on Bluetooth communication, and I want to use this. You might probably discover here is a pin code, which I have to enter now, 31, if I got right, 58, yes. So I have now access with my mobile phone to this. And now I have all my heating commands on this on my laptop or on my mobile phone, however. And if I want, for instance, to modify the temperature, so set point is currently 19 degrees. It's same like here. You can do it either here, yeah, or you can, for instance, do it in such a way. You see, you have a remote control. You can operate from comfort to standby. However, comfort, standby, one step back. So we have here comfort mode. I turn now with the mobile to standby, or I'm leaving home, for instance, go to eco mode, so you can do everything. So you have plenty of options. Taban is really a perfect partner in regards of heating control. We do have really a widely range of heating actuators, heating controllers, and if you need more details, so we are happy if you got back to us. Hopefully it was good for you. We could share some interesting insights with you, and you'll find this recording in the next couple of days on our Taban webpage, recordings on the German webpage and on the English webpage as well. And I want to mention or to remind you, we will definitively have a new seminar, a new webinar in meanwhile, but in May we will definitively have a specific webinar with the content, brand new sensors from Taban, optic based. Stay eager. See you next time.